Okay, so now we've really come to what I consider the heart of the normalization. This is the point where we have to convert raw moles into normalized moles, and the normalized moles essentially are what the atoms per formula unit in the formula are, and so that really is the sort of really the meat of this normalization. Now, one thing that I'm going to do a little differently than I originally planned is if we look here, we'll see that these are the different normalization schemes we're going to use. And I'm going to talk about these more in a moment. But what I want to do first is because I'm going to be doing some calculations over here with these different normalization schemes. I don't want all these numbers as I'm kind of going through the example to all end up being zero or divide by zero errors or something like that. And so although I said earlier that I was going to not kind of copy this row down until later on, I have changed my mind and I am going to copy this row down for at least for the test analyses here, because I want to make sure that we get real numbers in the normalization portion. So I'm just going to copy these here for the little set of basic test formulas that I have. Those up there will actually worry about these tests, the Gedrite and the Ferry Gedrite and the Cursitite a little later on. What I'm primarily interested right now is ensuring that I have a set of numbers that matches, that goes along with each of these different normalization routines, and so we actually get real numbers instead of numbers that won't mean anything to you if you're looking at it. It's like, well, what does divide by zero mean? Well, it doesn't, it's not helpful. So let's take a look at these normalization schemes, and again, we're going to start with this top one first. So the way that I have this set up is this first column here is essentially just a label, okay? And these are the 6 different normalization schemes, and these are the cation-based normalization schemes, and so they are actually based on the cations that we measure. And the 6 different ones are, there's one that's called 16, and I will explain that in a moment, but essentially here's the explanation. Then there's one that's called 15EK, which means 15 excluding potassium. Then we have 15ENK, which is 15 excluding sodium and potassium. Then we have 13CNK, which is 13 excluding calcium, sodium, and potassium. Then we have 8SiAl, 8SiAl, which is 8 tetrahedral cations that include silicon and aluminum. And then we finally have 8Si, which is 8 tetrahedral cations that only include silicon. Okay. And I've ordered them in this way, again, because I think that this first one, although there's a certain complexity to it, may actually be easier for beginners in normalization to kind of consider. So again, this is the label. This is the description, and we can kind of look at the descriptions really quickly. So 16 here refers to that the tetrahedral site, the 6 coordinated sites, the 8 coordinated sites, and the alkali sites, all in total add up to 16. And if you take a look here at the formula, you'll see 8 plus 5 plus 2 plus potentially up to 1. And that all adds up to 16. Okay, so that means every site is filled and no vacancies are allowed, including no vacancies in the A site. Okay, so that is one potential normalization routine for amphiboles. And we'll see later that this will work for some amphiboles, this will not work for other amphiboles. Okay, we'll just kind of quickly go through the rest of the list here. 15 excluding potassium. What that is that we have the tetrahedral site, the 6 coordinated site, and the 8 coordinated site all equal to 15. So you can see that it's the T, the 6 coordinated M, and the 8 coordinated M, and we're ignoring the alkali site. So we're saying that just these, the 8, the 5, and the 2, add up to 15. and we're excluding potassium, which has to be in the A site, but we are including sodium, which means that we're not going to allow any sodium to be in the A site. We're forcing all of the sodium to be in the 8 coordinated M site. Okay? But obviously that is not necessarily how an amphibole has to be, right? It's possible that there may not be any sodium in the 8 coordinated site, and in fact all of it may be in the A site instead. And so that is what this next normalization routine is. And in fact, that's why this pair is kind of lumped together, because they're somewhat related to one another. And in this case, we're excluding, it's 15, excluding sodium and potassium. So again, we have the same 15, T plus 6 coordinated M plus 8 coordinated M. And again, it contains silicon and aluminum and titanium and iron and magnesium and calcium. But it excludes sodium and it excludes potassium, which means that all of the sodium and potassium have to be in the A site. So you can see that those are two N members. And I've kind of offered, an example here where, in glaucophane, for example, we would expect probably in N-member glaucophane that all of the sodium really would be in the A-coordinated site. Whereas in an amphibole like etonite, in the N-member formula, we would expect that all of the sodium would all be in the A site. Okay, now in real life, this may not be entirely true. And so what we'll see again is that sometimes these normalizations work and sometimes they don't work so well. And that's why we have the flexibility of having, six of them to work with. Okay. The next normalization scheme is 13 E, C, and K. Now, in this case, we are not concerned with what's going on in the 8 coordinated site, and we are only concerned with what's going on in the 4 coordinated tetrahedral site and in the 6 coordinated metal site. And again, these add up to 13. You can see that essentially 1 plus 7 is 8, plus 4 plus 1 makes 13. So 5 plus 8. Okay? And because we include iron and magnesium in this, we're only excluding calcium, sodium, and potassium. That forces calcium, sodium, and potassium to be distributed among these two sites, but it also doesn't permit any magnesium or iron to be in this site. So we will find that sometimes this works quite well, but for example, if we look at an amphibole like Gedrite down here, or the fairy Gedrite, we would see that that would not be a very good normalization scheme, because obviously we would want to put magnesium into that site. Then again, now we have our last two normalization schemes where we have, here we're only concerned about the occupancy of the tetrahedral site. We see that the tetrahedral site is equal to 8. You can see again up here in the formula 8. And there are two N-member possibilities here as well. One would be that we include aluminum in that 8, which means that all of the aluminum has to be in the tetrahedral site, and none of it is allowed to be here in the 6 coordinated site. Okay, so that's the this 8 SiAl. And the other possibility would be that the tetrahedral site only contains silicon, and it forces all the aluminum, or any aluminum that's present, to be in the 6 coordinated metal site. So that is the other limitation. So, and again, I have aluminum highlighted in the etonite and glaucophane to kind of show you examples of both of those N members. So these are the 6 different possible ways of normalizing an amphibole. And again, we are going to discover as we normalize our unknown mystery amphibole down here, and indeed maybe even some of these additional test cases, that there will be normalization schemes that work among these 6. There will be normalization schemes that do not work among these 6. And in some cases, there will be multiple normalization schemes that work. Now, because of the sort of fake numbers that I've set up with these, the ones that, if there are multiple ones that work, we're going to see that they give the exact same result. Okay, but again, in reality, that isn't necessarily going to be the case, because once we have for example, iron in there, we'll see that the different normalization schemes will calculate a different ratio of ferric iron and ferrous iron. And we'll see that when we do the unknown mystery amphibole. Okay, so let's take a look at how these actually work. So the instruction here says that all of the sites have to equal 16. Okay, so we have these 3 additional columns over here. Let me get to them. We have actual cations, true cations, and normalization factor. Okay, well, the easiest column here to fill out is the true cations column, because this column, this number, has to be the same number as the number that's in this column here. And so the true cations in this first one here has to be 16. Okay? The true cations in both of these, we can see if we look here, it says 15 EK, 15 ENK. So both of these have to be 15. Okay? This one says 13 ECNK, so we are normalizing to a total of 13 cations, so this number has to be 13. And then finally, we see that both of these are normalizations to 8 cations. They're a different set of 8 cations, but they're 8 cations nonetheless. So both of these have to be 8. Okay, so that part's pretty easy. Now, this next part is the part that people have a little bit of difficulty with. This is the set of true cations, but now we want to know what the actual cations are that goes into those sites. And here's the thing. We have to follow whatever the rule here says. Okay, so I am going to do each of these 6 rules. And so we're going to put our equal sign here, and we're going to refer back to our raw moles in order to follow the rule. So the rule here says that all of the cations have to equal 16. And so what it tells us is that we have to use all of the cations. And so we're going to go back here to our list of raw moles, and we are going to add all the cations together. So let's progressively go through this. So do we add fluorine? No, we do not, because fluorine is not a cation. Okay, fluorine doesn't go in any of those sites. Fluorine is going to go into this site. So we don't include fluorine. How about sodium? Well, sodium definitely goes into one of these 16 different cation positions, and so we would include sodium. And likewise, we would include magnesium, and we would include aluminum, silicon, potassium, calcium, titanium, and iron. Those are all the cations. Okay? So we hit return, and we see that that is actually the value of all of the raw moles of all the cations added together. Okay, so let's go on to the next one here. So this instruction says we want all of the cations excluding potassium. Okay, so that's EK, excluding potassium, and we want them to be essentially, add up to our 15. And so we go back to our cation list here. And again, do we want fluorine? No, we don't want fluorine because fluorine is not a cation, so we skip that. We do want sodium, we want magnesium, we want aluminum, we want silicon. Now the instructions say exclude potassium, so we exclude potassium, but we do want calcium, titanium, and iron. Okay? So that's our next number. So let's do our next one here. Our next one says 15 excluding sodium and potassium. So we can kind of see how this is going. We don't want to include sodium or potassium into this normalization. And so we come back through here. And again, we exclude fluorine because it's not even a cation. We are specifically being told that we need to exclude sodium here, so we don't include that. We do want magnesium. We do want aluminum. We do want silicon. We were told to exclude potassium, so we will do that. We want calcium, titanium, and iron. Okay. See how that goes. You can pretty much see the pattern here. So here we are going to exclude, here let me move over a little bit. Here we are going to exclude calcium, sodium, and potassium. So same sort of thing. We don't want fluorine, we don't want sodium, we want magnesium, aluminum, silicon, we don't want potassium, we don't want calcium, we want titanium and iron. Okay, and then finally we have the last two. These are much simpler. This first one, we are only allowed to have silicon and aluminum. So we put the equal sign there, and we literally are only allowed to pick aluminum and silicon. That's all we're allowed to pick. And then finally, this last one says we are only allowed to have silicon. So this is the simplest one of all. The normalization is based entirely on silicon. Okay, so we now have the critical basis for our calculation. We have the true cations. We have the actual cations following the rules that are based in these normalization routines. And finally, we are going to calculate our normalization factor. And the normalization factor is the number that we are going to eventually multiply our raw moles by in order to get what our true normalized moles are. And it's essentially just a ratio. And so what we want to do here is we want to ratio, I see we got my AGU letter here. Hope that'll go away here in a moment. So we want to have the true cations divided by the actual cations. And so you see we get a number here that's, about 8.19. That's our normalization factor. And this is what's kind of interesting, is if we copy this to these cells, and I'm going to copy it in order to maintain the formatting. I'm just going to copy the formulas. Oh, didn't work. Never mind. Okay, so I guess I'll just copy that there. Copy that there. Okay, so the formulas didn't, I preserved the formulas, but I didn't preserve the formatting. Oh well. But you can see that all these numbers are fairly close to, fairly similar. 8.2, 7.8, 8.3, 8.1, 8.3, 7.8. So despite the fact that these numbers are very different, and these numbers are very different, then all of these have come out very similar. And so we'll see later on that this is where the variability in our normalization, in our different normalization routines comes in. Okay, so what I'm going to do is I'm going to temporarily skip this, and we'll go and do some of our site fillings, and then we'll come back and take a look at the charge balance.